Okay, now we're going to look at this module 2. Okay, the module 2 is about the microprocessor principle. Okay, the principle behind the microprocessor. Okay, so first we're going to look at the processor architecture. So this is the internal organization of a computer. Okay, so internal working of every computer can be divided into 3 parts. So each of the computer, as I mentioned in the previous module, okay, must have these 3 components. Okay, the first one is a processor or CPU, central processing unit. The second one is a memory. Okay, you need to have a memory for the data storage. And the third one is the input-output device or a GPIO. All right. So this GPIO can be for the input such as a keyboard, mouse, or sensors. This is for the okay. And then output such as LCD, printer, and monitor. Okay, so this is for the computers lah. What about embedded system? Embedded system also need to have these 3 components. Okay, first you need to have the processor, the CPU, and then you need to have a memory. Tak kisahlah sama ada is a RAM or ROM memory, and you also need to have the GPIO. Okay, for the input. Okay, in embedded system, what is the input for every embedded system? Okay, you have the sensors. Maybe you have the push button, the switches as the inputs. What about outputs? Outputs, okay, you can have the LEDs, the LCD display. Maybe we can have the 7 segments. Okay, so that is the outputs. Okay, so every computer must have these 3 things. All right, so what is this CPU do? Okay, so this CPU, okay, will control the operation of the computer, and it will perform any data processing. Okay, all the data processing will be done inside of this CPU. Okay, meanwhile, this memory is used to store and to retrieve the data. Okay, every time you're going to store the data or to retrieve any data, okay, that one is located inside of the memory. And meanwhile, input-output is to move the data between the computer and external environment. So input-output is used to communicate, okay, between your processor and the end user. Okay, to communicate between processor and user, okay, they will be going to use this input output. And next, how this CPU, memory, and input output is communicate from with one to another. Okay, there is buses here. Okay, a communication. This is a communication line is used to communicate, okay, between the CPU to the memory or memory to the CPU to input output to CPU, or input output to memory. So this bus is used to communicate among CPU, memory, and I/O. Okay, later we will see more details on this component. Okay, CPU, memory, input output, and then buses. All right, so now we look at this CPU, Central Processing Unit. Okay, so this CPU is used to control the operations, okay, of the computer and perform its data processing function, often simply referred to as a processor. So processor is equivalent to the CPU, okay, and used to control any operation inside of the computer. And at the same time, it will do the data processing. And this CPU, okay, you can, it is actually a brain lah for each of the computer. All right, which is it used to manage all the data process, all the operation inside it. Okay, and the CPU is used to execute information stored in a memory. So if you have a information that's stored in memory, that CPU will execute that information. Memory cannot execute the information, right? And The I/O device is used as a communication medium with a CPU. Okay, so as I mentioned earlier, okay, in order to communicate between the end user, okay, and the CPU, okay, we need to use the input-output devices. And this CPU, okay, is connected to memory and I/O through a strip of communication line or wire called buses. Okay, we have a total of 3 buses here. One is an address bus. Okay, so address bus is used to locate the input outputs lah. Okay, then we have the data bus. Data bus is used uh, to send the data either to from CPU to memory or from memory to CPU. And a control bus. Control bus is to control lah the data movement. Okay, either the data you need to be read or you need to be write. Okay, and next we're going to look at what inside of this CPU, because we know that this CPU used to do a data processing and to manage every operation. So inside of the CPU, okay, there are few register and component that you need to be familiar with. Okay, so we have a lot of components here inside of the CPU. Right? So here we have the registers. Okay, so the first register is, we call it as a program counter. Okay, so this is a program counter. So what this program counter do? So this program counter is used to point to the address of the instruction currently being executed by the CPU. So every time, okay, you're going to execute a program. Okay, this program counter will will point to that instruction. Okay, what the instruction that need to be executed. All right. Then we have the IR register. Okay, the instruction register. So this instruction register is used to store the instruction. Okay, read from the address of the instruction indicated by the PC. Okay, once the program counter take the address, okay, the IR register will store the instruction inside of this register. Okay, then we have the address register. Okay, so the address register is used to store the address of the current data. Okay, so if you have a data, that data will be stored inside. The address of that data will be stored inside of this address register. And last but not least, we have the data register, which is used to store the value of from the address indicated by the address register. Okay, so these are the 4 registers in the CPU that you need to know. Okay, a part of that, okay, there are 4 components that we need to know as well. First is a decoder. Okay, so this decoder is used to interpret the instruction brought to the instruction register and pass it to the control unit. Okay, so whatever instructions stored inside it in this instruction register will be decoded by the decoder. Okay, means that this instruction here, the instruction is usually in the assembly language, will be translated or will be decoded to machine language. Okay, 0101 binary representation by the decoder. Then after that, it will be sent out to the control unit. So this control unit will generate the control signal based on the instruction detected by the decoder. So the control units know lah what that instruction is going to do. Either you're going to do addition, okay, load a data, store data, or support. All right, and then we have the ALU. Okay, so this ALU is a stand for the arithmetic logic unit, and this ALU is perform any arithmetic such as plus, minus, divided, multiply, and logic operations. So every arithmetic and logic operation will be done inside of this ALU. Okay, and last but not least, we have the accumulator. Okay, so accumulator is a register that store the value used before and after an ALU operation. Okay, every time you do the LU, that result will be stored inside of this accumulator. So these are the components inside of the processor that you need to know. Okay, later we will see more details. Okay, how this components works. Okay, if you have this, for example, here, instruction here. Okay, how this instruction, okay, will be sent out through this processor here. Okay, later we'll see more details on that. Okay, next, we already look at the CPU. Okay, now we're going to look at the memory. Okay, the second component, okay, that must have in every computer system is a memory. So this memory is used to store the binary information needed by CPU. And there are two types of a memory. Okay, one is a ROM, read-only memory, and the other one is a RAM, random access memory. Okay, for the ROM, okay, it's a non-volatile memory. Okay, what is a non-volatile memory? Means that the content is retained even without a power. Okay, if you switch off your processor, whatever saved inside of this ROM will be retained. Okay, will not be erased. So in embedded system, so this ROM is used to store application program and test a subroutine. Okay, so this ROM is used to store your program. Okay, because you're going to write a program to do a certain task, and that program will be stored inside of this ROM. Okay, there are few type of ROM out there. Okay, which is we have a MROM. Okay, the mass ROM, PROM, programmable ROM, EEPROM, erasable PROM, and flash memory. And this erasable type can only be written a fixed number of time. Macam PROM and EEPROM, okay, the EEPROM can be rewritten a fixed number of time. Once, okay, you already written it multiple times, then after that it will be corrupted. Okay, and then next we have the RAM, okay, a random access memory. Okay, so it is a very volatile memory lah. Okay, what is a volatile memory? Okay, every time you switch off your processor, what happen? Data inside of that RAM. Okay, all the data inside of the random access memory will be erased. Okay, so the content will be lost without power, and it used to store a temporary data. So this is the functions lah of the RAM to store memory data. Okay, compared to the ROM, which is you're going to store the application program. Okay, the program that you're going to write will be stored inside of the ROMs. Okay, so in embedded system, very little RAM is required. Okay, some system doesn't have any RAM at all. Why very little RAM little is required compared to the computer? Okay, because computer, okay, you can see, okay, one computer will have the 60 gigabyte of RAM, 8 gigabyte of RAM, 32 gigabyte of RAM. What in embedded systems only have 1 kilobyte of RAM, 32 kilobyte of RAM. Okay, very little RAM is required. Why? Because, okay, your embedded system only going to run a dedicated function. Okay, since needed to run a dedicated function, so the data that you're going to store, temporary data you're going to store is not that big lah. Okay, compared to the computer, because your computer you need to run, for example lah, if you're going to do the video editing. Okay, video editing you need to have a very high RAM. Okay, so that's your program will not will run smoother. Okay, why? Because every time you do the editing, okay, it will be stored temporarily inside of the RAM. Okay, unless you save it to your hard disk, then after that it will be stored inside of the hard disk, right? So no limit to number of write and the device can handle. And there are two major type of RAM. Okay, we have the SRAM, DRAM. Okay, now we have the DDR RAM. Okay, we have the DDR, DDR2, DDR3, and DDR4. Right. So this for the memory. Okay, next we are going to look at the buses. Okay, why buses is very important lah. Okay, to communicate as a communication pathway between the CPU, memory, and the input-output. Okay, there are three types of a bus. Okay, we can see here. First is a control bus. Okay, so if you can see from this figure here, the control bus is a bi-directional. Okay, bi-directional means dua arah lah. Okay, it can go out and it can come into the CPU. All right. So this control bus is used to provide a read and write signal to the device, indicate if the CPU is asking for information or sending the information. Okay, if the CPU asking for information, means if the signal that will be sent is a read signal. Okay, if the CPU is sending information, okay, the CPU will be send the write signal, means that it's going to send the data from CPU to the input output, for example, to the memory, for example. Okay, so this is what the control bus do, okay, to provide a read or write signal according to the data that going to send the data or to ask for information. Okay, then we have the data bus. Okay, the data bus, as we can see here, also a bi-directional. Okay, and this data bus, okay, the size can be from 8-bit, 16-bit, 32-bit, 1 to 8-bit. Okay, later we'll see about this bit there. Okay, so what this data bus do? Okay, to carry information in and out of CPU. Okay, so the data that you're going to read or write, okay, will be sent using this data bus. Okay, if you're going to send the data to the CPU, to read the data to the CPU. So whatever, okay, that data will be sent using this data bus. Okay, if you're going to write the data to the memory, for example, from CPU to memory, so that data will be sent from the CPU to memory using this data bus. Okay, the more data bus available, the better the CPU, but more expensive. Okay, if you have high data bus, so what happens? Your CPU will become more faster. Okay, because you can send bigger size of data at the same time. Okay, but the more data bus size, your processor will become more expensive lah. Okay. The processing power of computer is related to the size of its data bus. Okay, for example, 8-bit bus can send 1 byte at a time. 16-bit bus can send 2 bytes at a time, which is twice as fast. Contoh, I give you a contoh. Alright, so we have this number here. Okay, we're going to send this number. Okay, let's assume that this is 16-bit number. Okay, and then we have two processor. Processor A, processor B. Okay, processor A is a 8-bit processor. 8-bit processor is actually referring to the size of the data bus. Okay, and processor B is a 16-bit processor. Okay, and this also referring to the size of the data bus. All right, so now we have a 16-bit number. All right, so for the 16-bit number, if we use it the processor A, what happened? Since the data bus of processor A is 8-bit. So what we need to do, okay, we need to divide this 60-bit number to 8-bit number. Okay, 8-bit, call it as a 8-bit chunk. Okay, so what happened? So divided into low byte and this is a high byte. Okay, on the first cycle, okay, the first value will be sent out to this data bus. Okay, this number here go to the data bus. And then the second cycle, okay, the second number, okay, which is the high byte, will be sent out through the data bus. So to send this 60-bit number, what happened? Okay, you need to have a total of 2 cycles to do it. What about if you have a processor bit, a 16-bit data bus processor? So for the 16-bit data bus processor, at the very first cycle, you can send out this value without any problem. Okay, you only require 1 cycle to send out this number bit data. All right, so that's why we call it this one here 2 times twice. Okay, because this one need to have 2 clock cycle, but this one only need 1 clock cycle. So what happens if you have a 32-bit data? Okay, let's say we tambah lagi. All right, we tambah lagi. Okay, now we have a 32-bit data. So what happened? For processor A, 8-bit data bus, okay, we need to have 4 cycles, okay, to send out the value. Okay, so 4 cycles to send out this 32-bit number. But for processor B, okay, we need to have 2 cycles. Okay, first we send the first 60-bit. Sorry. Okay, so first we send the first 60-bit. Okay, maybe we send this 60-bit. Okay, to the first cycles, and then next we send another 60-bit to the on the second cycle. Okay, what about if you have processor C, 32-bit processor? Okay, for the 32-bit processor means that okay, you can send this data here in 1 cycle. Okay, so now today we have a 60-bit processor. Okay, if you go to if you survey for your laptops or computer, okay, you can see okay 32-bit computer, 64-bit computer. Okay, what that 64-bit, 32-bit referring to? Okay, it referring to this data bus here. Okay, the size of the data that can be processed sent okay to the CPU in a single cycle. Okay, that's why 64-bit computer is more expensive compared to 32-bit computer with the same spec, right? All right. And last but not least is address bus. Okay, if you look at this address bus, okay, only have one direction from CPU to memory ataupun to I/O. Okay, so it's a unidirectional bus. Okay, and it is used to identify the device and memory connected to CPU. Okay, as a name implies, address. Okay, so address is used to identify. Okay, so each of the input output memory have its own addresses so that the CPU know. Okay, now I'm going to take the data from this address. Now I'm going to send the data from this address. So for a device to be recognized by a CPU, it must be assigned by a unique address. Okay, so every peripheral, input-output peripherals, memory have its own addresses. And this CPU put the address, okay, usually in a binary or something in the hexadecimal on the address bus, and the decoding circuitry will find the device. Okay, let's say lah. Okay, I'm going to use the printer. Okay, I'm going to print I'm going to print this document here. So what I need to do? Okay, so CPU will locate a printer. Let's say like the printer, this is a printer, and the address of printer is 0A. For example, this is HESA. So the CPU will send address 0A to the address bus. Okay, put this number to address bus. So what happened? Okay, the CPU will find, okay, now this it already find the address 0A, which is a printer, Then after that, okay, for the printing means that on the control bus, okay, we need to give a write signal because we're going to do a printing. Then printing means that we're going to write. Okay, once we're going to write, then after that we're going to send the data, okay, using the data bus to the printer, so that the printer will print out lah, whatever that you're going to print, right? So this is the use of the address bus to find, okay, to identify the device and memory connected to the CPU. Okay, if you're going to look at here, okay, this address bus also have a 16-bit, 32-bit, 64-bit wide. Okay, so means if you have a 60-bit wide, means that you have a lot of devices that you get connected to the CPU because the address is much bigger compared to 16-bit addresses. Okay, I give you a contoh lah, a simple contoh, right? So I have a 4-bit address and 8-bit address. Okay, so for 4-bit address, 4-bit, difficult to look at the difference. Okay. Okay, 2-bit address and 4-bit, 3-bit lah. Okay, 3-bit address. Okay, so for the 2-bit address, okay, so we have a 00, 2-bit Ingat lagi tak? Remember back 00, the combination of 2-bit number is 00, 01, 10, and 11. Okay, means that I only can connect to 4 devices. Okay, let's say lah, this is a printer. This is a memory. Okay, and then this is the LCD. And this address here is a LED, LED one. Okay, for the 3-bit, means that I can have 000, 001, 010, 011, 100, 101, 110, and the last one is 111. You can see here, when the address bus is bigger, now I can connect. Previously, I only can connect up to 4 devices. Okay, now what happened? Okay, I can connect to 8 devices. Okay, starting from here, this is a printer, memory, LCD, LED, LED2, switches, push button. What else we have? LED3 7-segment display. So now I can connect up to 8 devices. Okay, by using a 3-bit address bus. Okay, while 2-bit address bus only can support up to 4 devices. Okay, and if you have a 64-bit, what happens if you have a 64-bit? Then you can have a lot of devices to connect it to your CPU. Okay, because each of the device will have their own unique address bus. Okay, so for example, address 00 will not be shared, okay, with printer and memory. Memory and printer will not share the same addresses. Okay, each of these devices will have their own address. Okay, so that's it for the component of the CPU. Okay, and last one is input output lah. Okay, the input output is the input output is input device such as LED, input device such as switch, keyboard, okay, and push button, while output device is such as printer, LED, okay, which is used to display the information. Input device is used to give the information from the end user to the CPU. Any question up until here? Ada soalan tak from you guys? Okay, before we go to this slide here, how the CPU works. How the CPU works. Okay, so this is the basic CPU. Okay, there are have three phases of execution. Okay, first is a fetch. Okay, the fetch is where the instruction is fetched from the memory. Okay, but to the CPU. All right, then we have the decode phase. Okay, which is this where the instruction that been fetched earlier it will be interpreted into the binary instruction because the CPU only know machine codes. Okay, since this the instruction is in C programming or in assembly language, so it need to decode it. Okay, it need to interpret into the binary instructions. Then after that, the third one is a execute. Okay, which is the CPU will perform the request action. Okay, so this is the basics. Okay, the uh, the basic cycle for each of the CPU. Okay, to execute a certain instruction. Right, first we need to fetch. Then after that, need to do the decoding process, and then it need to execute the process. Right. So here, now we're going to look at these examples lah. Okay, we're going to look at these examples how the CPU will execute this program here. Okay, so we have two programs. This is a C program. This is the assembly language. Okay, and by looking at this program, you can see C programming is more direct lah. Okay, you can see here. First, you put okay in A equal to 1. Okay, then after that, another variable B equal to 2. And then next is C equal to A plus B. So by looking at this C version, we know that, okay, we're going to add 1 plus 2 and put the result to C. Okay, so this is what happened inside of the C version. Okay, in the assembly language, so what we need to do here is, okay, we need to do the same thing, okay, which is to add A plus B and put it to C. Okay, put the result into C. So what happened here is, okay, for assembly language, okay, each of this number, okay, you need to put it inside of the memory, okay, inside of the address. Okay, so that's why you can see this is where the first one, okay, you load A equal to 1. Okay, then after that, you load B equal to 2 at the second instruction. And at the same time, okay, you're going to add them together. And last one here, store to address 2004 means that you're going to store the result to C. Okay, and this is explanations lah. What the load 2000 do, okay, which is you're going to load A to a data register inside of the CPU. Okay, recall back. Okay, we have the inside of the CPU, we have this register here called a data register. Okay, so this is a temporary data. Okay, which is you're going to store the data temporarily because before you do the ALU process. Okay, so every time you're going to load the data from the memory to the CPU, that data will be stored inside of this data register. Okay, next we have the ADDOX2002. So what happened here is, okay, after we load the A, and then we're going to load the B. And next, add them together, and the result will be stored in the ACC. What is an ACC? Accumulator. Okay, recall back in the CPU, we have an accumulator. What this accumulator do? To store the result from ALU process. Okay, every time you do the ALU, that result will be stored inside of the accumulator. And last but not least is store OS 2004. Okay, this is where you're going to save the added result to the address of C. Okay, which is equivalent to ni lah. C equal to A plus B. The good thing about C version, okay, you no need to know what is the address for this variable. Okay, no need to know. Okay, you just what we call here, you just create a variable, initialize it, then after that you can use that variable. Compared to assembly language, you need to know where is the number one is coming from. What is the address of number one? What is the address for number two? And what is the address of for number C? You need to know the architecture behind of the processor. Then after that you can write the that. So that's why for assembly language, okay, you need to study the architecture of the processor. C programming, no need to study the architecture. Okay, you can simply write the program and the program will do it for you. Okay, to find where is the number one, where is the number two, and where you're going to put inside of the C. All right, so we assume that we have this instruction. Yeah. Okay, so this is instruction. Okay, we have 3 instructions. So this is the first instruction, load. Second instruction, add, and this is the third instruction, store. Okay, now we're going to look how the CPU works. Okay, the first instruction, this is the first instruction, the load instruction. Okay, so this instruction, as I mentioned earlier, all of the program will be stored inside of the program memory, inside of the ROM. Okay, this is the program memory. Okay, on top of here, this is what we call it as a program memory. Okay, so every program will be stored here, and then below here is a RAM. Okay, we have the ROM, program memory, and RAM. So this is a non-volatile, this is a volatile memory. Okay, so now we're going to look how to first take this first instruction. We have 3 instructions here. Load 2000, add 2002, store 2004. And this instruction is stored inside of this address. Okay, program memory address. Okay, the first instruction stored at the address 1000, the second one 1002, and the third one at address 1004. Okay, so here we look at the first step. Okay, the address the CPU want to execute is located at address 1000 in the PC. So since this is a program memory, the program counter point to this address. Okay, this is a PC. Program counter point to this address. Okay, next, take this address and put it inside of the address register. Okay, so program counter point to address 1000. Take the address, put it inside of the address register. So when this address 1000 enter the address register, it will automatically access to the address 1000 in the memory. So once the address 1000 inside of the address register, okay, this components here will directly find where is the location of the address. Okay, once it get the address here from this program memory, okay, from the memory, okay, the instruction inside of this address will be read from the memory, and then it will be stored to the instruction register. So this is what happened in step number 5. Okay, instruction is stored in the instruction register. You can see here load 2000, which is located at address 1000, now is stored inside of the instruction register. Right. Then step number 6, this instruction goes to the decoder. Okay, it will send out to the decoder for the decoding process. Okay, to change from this assembly to binary format or to machine code. So once this instruction sent to the decoder, the program counter, okay, now you can see here the program counter is increased, pointed to the net address. You can see the net address 1002. Now the program counter point to 1002. No longer point to 1000, now point to the new address. Okay, then after that, the decoder interprets, okay, what the content inside of this instruction here, okay, and the control unit understand that, okay, the content says that, okay, we need to load a data from address 2000. So control unit will find where is the address 2000, go to address 2000, which is here, take the value inside, okay, you can see 1, put it inside of the data register. So this is what happened in step number 10. Okay, the value of the data register is evaluated to any circuit needing it. So number 1 from this address 2000 will be put in inside of the data register. Okay, since the value may be operated through LLU, so it will also temporarily store inside of the accumulator. Even though we're not using the ALU yet, okay, the same data will be stored inside of the accumulator. So this is what happens when the first instruction is executed. Okay, so step number 11 is the last step lah, after the first instruction is executed. Okay, next. Okay, now this is the second instruction. Okay, so previously the program content is increased from 1000 to 1002. Betul tak? Okay, so what happened here is this address will be sent to the address register, and the address register will find, okay, 1002. Where is the 1002? Okay, still inside of this program memory. Okay, load the instruction ADDOS 2002 into the instruction register. Okay, so that's why you can see ADDOS 2002 now is be put inside of the instruction register, and then this instruction will be interpreted by the decoder. Okay, will be sent out to the decoder for the interpretations, and at the same time the program counter is increases. Okay, now your program counter see from 1002 now point to address 1004, which is for the next instructions. Decoder, okay, will translate this instruction to binary representation or machine code, and the CU know, okay, now we need to add the previous value with this number here. So what happened? CU go to address 2002. Okay, 2002, this is the address 2002. Take the value 002 here, put it inside of the data register, and then due to this ADD is an addition. So what happened here is arithmetic logic unit will be perform the addition. Okay, we have the number 2 plus with 1 produce 3. Okay, the result is 3 will be stored inside of the accumulator. Okay, so this is after the ADD instruction is executed. Any question up until here? Ada soalan tak? Okay, next. For the store instruction, okay, you can see program counter point to address 1004. Okay, it will put this address to the address register. Address register will find where is address 1004. Okay, inside of this address 1004 have another instruction, store 0x2004. So this instruction will be loaded into the instruction register. Okay, then after that, the instruction register will pass this instruction to the decoder for the decoding process. And at the same time, your program counter now point to the next address, 1006. Right? And once the decoder is translate the store 2004 to machine code, the controller unit know, okay, now we need to store, okay, the value, previous value to this address 2004. So it will go to the accumulator, take the results, and find address 2004. Okay, you can see this is the address 2004. And next, what happened? Put number 3, because the number 3 is coming from this accumulator. Put it to the address 3, which is this is a C lah. Okay, this is the C, address 2004. Okay, next, that is where the store instruction has been finished. Okay, the next cycles. So program counter have address 1006. Okay, now it has address 1006. Put it onto the instruction register. Address register 1006. Okay, yeah, I put yeah. Okay, so now it's a 1006. So what happen? Go to address 1006. But in this address 1006 doesn't have any instruction. So what it mean? So no instruction means that the program is already finished. Okay, no need to load any instruction to the instruction register. So the CPU know, oh, now the program has ended. Okay, we just stop here. Okay, so this is how the fetch, decode, and execute cycle happens. Okay, fetch, where the program counter fetch the instruction from the program's memory to the instruction register. Decode, where the decoder is used to decoding to translate this instruction to the machine language so that the control unit know what it's going to do. And its execute will be done under this ALU here. Okay, ALU and accumulator. Ataupun including the data register and the memory. Okay, so that is for the fetch, execute, and fetch, decoding, and execute cycles. Okay, any question before we go to this pipeline? Ada soalan tak from you guys? Okay, I will take some time, sir. I will take around 10 or 20 minutes, 15 minutes, okay, to finish, okay, this slides here. Right, so now we're going to look at the pipeline. Okay, what's a pipeline? Okay, this is a concept of the pipeline. So pipeline is a technique used to enhance the execution speed of an instruction by dividing the process of an instruction into multiple stages. Okay, so each stage process a part of the instruction and pass it to the next stage, allowing multiple instructions to be executed simultaneously in an overlapping manner. So this pipeline concept means that okay, you're going to do you're going to run a program simultaneously. Okay, instead of execution one instruction at one time. Okay, such as previous one, from start to the finish. Okay, before we beginning the next instruction, pipeline will allow multiple instructions to be processed at different stage simultaneously. Means that okay, when you for example, here where you do the decoding, maybe the next instruction will be fetch. Okay, that is a pipeline. Means that more than one instruction will be executed simultaneously. Previously, we do first instruction. Okay, what happened previously? Okay, we execute this one here, the load. Then after that, after the load finish, then after that we do the addition and store. But now, while using the pipeline, okay, we do the load, add, and store simultaneously. Okay, there are many type of pipeline. Okay, the first one we use a simple one lah. There's three-stage pipeline. Okay, the three-stage pipeline is fetch, decode, and execute. All right, so it's a simple form of instruction pipelining. Okay, and each stage, okay, will perform a specific task, and multiple instructions can be processed simultaneously in overlapping manner. Okay, contoh previously. Okay, without a pipeline. This is without a pipeline. Yeah? No pipeline. What happened? Okay, first. Okay, I draw it like this. Okay. So let's say like this is a time frame. Okay, we assume that, okay, we have fetch, decode, and execute. Okay, and we assume that each of these here take one cycle. Okay, one cycle to execute. Right. So here is a number one, cycle 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. First, we have the first instruction. Okay, load OX 2000. Okay. So here, what happened here for the load OX 2000? Okay, we need to have a fetch, decoding, and execute. Okay, so means that until cycle number 3, the first instruction is finished. Okay, once this one is finished, then after that you can do the second instruction, ADDOX2002. Okay, so it starts on the fourth cycle. First we fetch, then we decode, then we execute that instruction. Okay, on the 6 cycles, okay, the second instruction already finished. Okay, and here we have another instruction which is a store OX 2004. Okay, and this store OX 2004 will be started after the second instruction, which is AADDOX 2002 is finished. So on the 7 cycles here, okay, we fetch the instruction, we decode the instruction, and we execute this instruction. So by not using a pipeline, so the total cycles needed is 9 cycles. Okay, to execute these 3 instructions. Okay, you can see here these 3 instructions. You need a total of 9 cycles to execute it. Okay, meanwhile, if you're using a pipeline, okay, so pipeline. Okay, I draw this one here. Okay, so this is a 1, 2, 3, 4, 5 right now first. Okay, first, do OX 2000. Okay, first we fetch. Okay, next. On the second cycle, the first instruction is now do the decoding process. And at the same time, this is why you use a pipeline. Pipeline, the second instruction will be fetch. Okay, you see here. Okay, first instruction, do the decoding process. And the second instruction is being fetch. Okay, on the third instruction, on the third cycles, first instruction finished, second instruction now go to the decoding process, and now at the same time, okay, we can load the third instruction. You can see here, 3 instruction is execute simultaneously. Okay, so on the fourth cycle, okay, this one is execute, and the store is decoding. Okay, if you have another question, another instruction down here, and it will be fetch lah. Okay, while at the fifth cycle it is finished. Okay, the store instruction is finished. Now you can see here a total cycles needed to execute these 3 instructions using a pipeline is only take you about 5 cycles. Compare without no pipeline, okay, will consume 9 cycles. Okay, so means that pipeline, okay, in terms of performance, okay, execution time is much shorter lah compared to non-pipeline. This is for the 3-stage pipeline. Okay, next we have a 5-stage pipeline. So the instruction execution step can be refined to increase the number of pipeline stage into here. Okay, stage 1, we fetch. Stage 2, we decode. Stage 3, okay, fetch the operand. Stage 4, execute stage 5, okay, write back. Okay, contoh lah, without pipeline. Okay, the blue color here, this is the first instruction. The purple color is this is a second instruction. Let's say you have two instructions here. One is a load, and then we have number 2 is a ADD lah, for example. Okay, so first we need to load. Okay, because this is a 5 stage. Okay, so first cycle load, second cycle decode, third cycle fetch, operand fetch, fourth cycle execute, fifth cycle you need to write the result. On the sixth cycle, then after that we can fetch the second instruction. So you can see here, if we non-pipeline, okay, it will cost you 10 cycles, okay, just to execute 2 instructions. Okay, this is for the non-pipeline. But if you use a pipeline, okay, it will cost you only 6 cycles. Okay, 6 cycles to perform these 2 instructions. Okay, this is why you need the pipeline. So now we're going to look at how to calculate the performance for each of the pipeline. Okay, so the performance of a pipeline is typically measured using a speed up, okay, throughput, and latency. So this is how you're going to measure lah. Okay, whether your system, okay, have a high performance or not. Okay, so what is a latency? Latency is the time taken to complete a single instruction from start to finish. Okay, so from start to finish to complete one single instruction. While throughput is the number of instructions completed per unit time. Okay, given the time, okay, so now you're going to find out how many instructions that you can complete in that given time. That is a throughput. Meanwhile, speed up is a measure how faster a pipeline processor is compared to a non-pipeline. Okay, you're going to compare lah between pipeline and non-pipeline. Okay, what is the speed up? Is it a 2 times faster, 5 times faster, or is it a same speed? Okay. So the speed up can be calculated based on this formula here. Okay, S equal to execution time without a pipeline divided by the execution time with a pipeline. Okay, you take the execution time without pipeline, divide with a pipeline. Then after that, you get the speed up. Macam tadi, like we did earlier. Okay, 10 without pipeline, 6 with a pipeline. So 10 divided by 6, okay, you will get that number. All right, so maybe around 1.8 something. Okay, speed up 1.8 something. Okay, or number of cycles without a pipeline divided by a number of cycles with a pipeline. So this is actually a ratio lah. Okay, without a pipeline divided with a pipeline. Okay, now we're going to look at this example. Okay, given that you have this 5 stage, okay, of pipeline, okay, fetch, decode, execute, memory, and write back. And this is the time taken, okay, for the fetch, okay, needed a 4 nanosecond, decoded 2 nanosecond, execute 4 nanosecond, memory 4 nanosecond, and write back 2 nanosecond. So this is for the one instructions lah. Okay, we have a 5 stage, okay, one instruction. All right, for the what we call non-pipeline, okay, so first we're going to do a fetch lah. So fetch will cost you 4 nanoseconds. Okay, then after that, decode. Okay, this is the second stage. Decode will cost you 2 nanoseconds. Execute 4 nanoseconds. Memory 4 nanoseconds. And write back is a 2 nanoseconds. Okay, now we're going to find out what is the latency. Okay, so latency, what is a latency? Latency is a time taken to complete single instruction from start to finish. Okay, for these examples here, the latency is started from here, 4 plus 2 plus 4 plus 4 plus 2 equivalent to 16 nanosecond. So you already get the 16 nanosecond. So to execute one instruction, the execution time or the latency will be 16 nanosecond. If you have two instructions, the execution time will be, okay, so this is for the instruction number 1. This is for instruction number 2. Execution time sama dengan execute time. Okay, 32 nanoseconds. Okay, so this is for two instructions. Okay, execution time for two instructions will be 32 nanoseconds. Okay, so this is for non-pipeline. Okay, later we'll see the throughput as well as the speed up. Okay, so this is for the pipeline. Okay, we assume that the same, okay, the same stages with the same time here. Okay, 4 nanosecond, 2 nanosecond, 4 nanosecond, 4 nanosecond, 2 nanosecond. Okay, so for the pipeline, since we're going to do a pipelining, okay, the first step that you need to do is, okay, you need to make sure that this time here is same across all of the 5 stages. Okay, you need to have a same same times. Okay, same execution time for each of the stages. How to get to make the time here is what we call same across of these 5 stages. Each you need to find out the what is the longer or the largest time of the maximum time, okay, of from this 5 stage. Okay, the maximum time from these 5 stages is 4 nanoseconds. So what we need to do here is, okay, so we need to make the decoding process also 4 nanoseconds and white byte also 4 nanoseconds. So that's why you can see here, fetch, okay, will cost you 4 nanoseconds, decoding 4 nanoseconds, execute another 4 nanoseconds, memory 4 nanosecond, and write back will be at 4 nanosecond. And now the latency is equivalent to 20 nanosecond. Previously, latency only cost you 60 nanosecond. Okay, but pipeline now the latency is 20 nanoseconds. Okay, next, okay, we're going to find out what are the throughput. Okay, find out the throughput. Okay, for 32 nanosecond. Okay, what are the throughput for 32 nanosecond? Okay, so here, what we need to do here, okay, we can see, okay, for the duration of 32 nanoseconds, okay, you can execute how many instructions? 1, 2, 3, 4. Okay, 4 instructions. Instructions can be executed, okay, for a period of 32 nanoseconds compared to non-pipeline, only 2 instructions can be executed, okay, for a duration of 32 nanoseconds. You can see here, this is the first, cost you another 60 seconds and 16 seconds. Then the second instruction cost you another 60 seconds. So total 32 nanoseconds. Okay, you only can, for the non-pipeline, only execute 2 instructions. Okay, while this one is of 4 instructions. So this is a throughput. Okay, how many instructions that you can manage to execute given a certain period of time. Okay, what about the speed up? Okay, speed up sama dengan non-pipeline divided by pipeline. Okay, you have a non-pipeline just now. Okay, if you can see here, all right, the speed up will be 2 times. Okay, because this is a 4 instructions and this is only 2 instructions. So the speed out will be 2 times. Okay. So this is how to to calculate the performance for the pipeline with a non-pipeline. Okay. So here again for the pipeline, what you need to do, you need to make sure that each of the stage have the same duration. Okay. So how to get make it a same duration? Find the maximum time. Okay, for the stage, and make it normalize for each of the stages. Okay, contoh. Alright, so this is to calculate the speed up. Okay, so which is to measure how much faster a pipeline process is compared to a non-pipeline one. Alright, so examples here. Assume we need to execute 100 instructions. Okay, for example, okay, what we call it. We take a 5-cycle, a 5 stages of pipeline, and then if on the stage will cost you 1 cycle. All right. So here for non-pipeline execution, total cycle will be 100 multiplied by 5 equal to 500. Okay, sama dengan 500. Okay, because okay, we're going to execute 100 instruction. Okay, one instruction costs you 5 cycles. Okay, so now the total execution time is 500 cycles for the non-pipeline, and for the pipeline, okay, this will be the formula. Okay, total cycle equal to 5. Okay, 5 is the latencies lah. Okay, the instruction execution time for one instruction plus 100 minus with 1. 100 is the number of instruction minus with 1 sama dengan 104. Okay, so you get 104 divided with 500. Okay, 500 divided by 104 sama equivalent to 4.8. Okay, now we're going to find out what is the speed up earlier. This one. Speed up. Okay, so first, okay, we take a 2 instructions lah. Okay, for the 2 instructions. What is the execution time for the 2 instruction? One instruction costs you 60 nanosecond. Okay, multiply by 2. Okay, you will get 32 nanosecond. Okay. So this is for non-pipeline. Execution. What about execution for pipeline? Okay, equivalent to, okay, one instruction costs you 20 nanoseconds. So 20 nanoseconds. Okay, sorry. Down. Okay, plus, okay, just now 2 minus 1, and then because tadi one stage is 1 cycle. But this one here, one stage is 4 nanoseconds. So you need to include the 4 nanoseconds here. Right, so sama dengan 20 nanoseconds plus 1 multiplied by 4 nanoseconds. Okay, you will get 24 nanoseconds. Okay, and then 32 speed up is 32 nanoseconds divided by 24 nanoseconds. Okay, then you get the speed up lah. The speed up for 2 instructions, okay, will cost you around roughly 1 point something. Okay, let's say if for let's say if you're going to execute 4 instructions. Okay, so for the 4 instructions, 16 multiplied by 4, you will get 64 nanoseconds for non-pipeline. Okay, and 64 nanoseconds divided by 24 nanoseconds. Okay, you will get around berapa? Okay, 3 something. Okay, so this will be the speed up. Okay. Okay, based on this formula. Okay, 5 plus 100 minus 1, and then you need to multiply with the ni lah, dia punya one stage equals to how many times? Okay, suppose this is the formula. This is the formula. Okay, and then this is the examples. Yeah, I already mixed up that one. All right, and then next is okay, we're going to finish the pipeline. Okay, we have the latch delay. So what is a latch delay? In a pipeline processor, a latch or register is used between the pipeline stage to store intermediate result and synchronize operation. All right, because to do a pipeline, a latch is required in between the pipeline stages. Okay, those need to consider the delay produced by latch. Okay, why latch is used? Okay, because we're going to uniform the duration of the stages here. Okay, ideally, okay, the latch delay is 0. But in a real world, this latch here, the delay, okay, there will be a delay for each of the latch. So you need to consider this latch in your calculation. So the latch delay refers to the extra time required for a data to be transferred and stabilized in these latches before the next stage can be processed. Okay, so this is the calculations lah. Okay, this is the delay of the latch. Okay, duration of the latch, and here started from here to here, this is the TM max, maximum time of the stage, and T here is actually the duration after you consider the latch. Okay, so here T equal to TM tambah T. Okay, this is after you take the delay into consideration. If the D is 0, so then T sama dengan TM. So how to get a frequency? Frequency sama dengan equivalent to 1 over T lah. Okay, the T is coming from here. Okay, so this is the limitation of the pipeline, right? First, even though the pipeline improve the performance, okay, it also introduce some challenge, okay, or limitation. Okay, one of the limitations here is the pipeline hazard. Okay, so a pipeline hazard is a situation that cause delay or incorrect execution of the instructions. Okay, there are 3 types of pipeline hazard here. The first one is a structural hazard. Okay, which is 2 instructions attempting to use the same resources at the same time. Okay, that is pipeline hazard because we have two instructions and both instructions going to use the same resources. Okay, for example, in the single memory architecture, such as a von Neumann, okay, fetch and execute cannot happen simultaneously. Okay, that will trigger the structure hazard. Then we have the data hazard, okay, which is a data dependencies, and instruction depend on the result of the previous instruction that hasn't completed yet. Okay, means that you run instruction number 1, and then at the same time you run instruction number 2. But instruction number 1, the instruction number 2 going to use the value from the instruction number 1, but the instruction number 1 is not yet executed. Okay, so that's what we call it as a data hazard due to data dependencies. And last but not least is a control hazard, okay, which is happen in the branching problems. The processor does not know the next instruction due to the condition branch. Okay, and the second limitation is a pipeline stall loss due to the bubbles. Okay, when a pipeline stops progressing due to the hazard, it inserts a stall bubble, which is a cycle where no useful work is done. And more stalls will reduce the performance gain from the pipeline. For example, here, right? So this is a normal execution. You can see here for the normal execution, okay, these are under the pipeline. Okay, you can see there is no bubbles here. But if there is a stall here, okay, it will produce a bubble, and you can see instead of the execution ended at 9 cycles, now it's 8 cycles. Now, due to this bubble here, stall here is now extended to 9 cycles. Okay, to end the instruction. Okay, and the third one is increased complexity and power consumptions. Okay, so pipeline requires more control logic to manage hazard and forwarding. So it will increase CPU design complexity. Okay, if you use a more pipeline register, will increase more power consumption and will reduce energy efficiency. And last but not least is an unequal stage delay. Okay, so this is the pipeline balancing rule. Okay, if the some pipeline stages takes more time than others, so the longest stage determine the clock cycle time. Macam tadilah. Okay, like here, what we did earlier. Okay, we doesn't have a uniform period for each of the stage. So what happened? This 2 nanoseconds, we need to expand it to 4 nanoseconds. Okay, so that is a limitation of the pipeline. Okay, any question up until here before we stop?